Good morning. Good afternoon, ladies and gentlemen, and glad to be talking about some stuff here, which is outcome of some of my dissertation students who did research works on these two topics. And the title here is Potential of Innovative Solar Energy Technologies. And there are two pieces in it. One is to do with solar roads, another is to do with solar paints. Then both are at different stages of technological development. And I thought, right, okay. And I'll be going through both of them one by one. And yes, please go to the next slide, please. Right, good. So, introduction to solar energy. Yes, please continue. Yeah, keep going. Yes, we can stop there. Right. So the idea is that the global surface area, the world that we occupy, is 196.9 million square miles. Out of that, the land area, excluding obviously oceans, seas, and other water, surface water, lakes, and alike, 57.5 million square miles is the land area, and that is the one which is occupied by humans. 8 billion roughly is the population, and out of that 8 billion population, 93 percent occupies those areas of land where solar energy can be exploited or harnessed. And the range we are talking about is, yes, please, again, Claire. So the solar energy ranges between 3 to 5 kilowatt hour per day, reaching, as in solar irradiance, reaching the Earth, and 4 million exajoules energy reaches the Earth's surface. So that is the total, if you talk in energy context, exajoules per year. Now, out of that, 0.1%, even if 0.1% of the solar radiance reaching the Earth could be harnessed with only 10% efficient technologies, only 10%, the result can be, yes, please, Claire, 150% times of global energy demand can be met. So way more than it is needed. So that's the potential that solar energy has, which reaches from the sun to the earth in solar irradiance form. Yes, please continue. Right. Now, solar power and the UK. One of the oldest renewable energy resources. It came about in 1939, about 80 years or so ago. The UK has increased its solar energy capacity by another 177 megawatt in 2021. All the references are towards the end of the slides. Now, solar energy still at the moment, solar energy, despite this 177 megawatt additional capacity, which was induced in the UK in 2021, despite of that, the UK is still generating just about 4% of the total UK energy demand from the solar energy. So there is huge potential to expand and excel in that area. Now, the transition rate, so transforming our energy resources or switching ourselves from fossil fuel and other energy resources towards solar energy resources, if we continue, we will have to continue at a rate of 2.6 gigawatts per year. That's the rate of transition required if we want to achieve the target of 40 gigawatt solar capacity by 2030 in the UK. Thank you, Claire. Yeah, please. Right. That was the preamble. That was just the background. Now I'm going to cover these two individual pieces of research, solar roads, and after that I'll be talking about solar paints. So let's talk about solar roads first. The student who is the principal investigator, his name is Mr. Mukherjee, and studying at Northam University, master's degree program. The other student is Jennifer Bennett and Kelechi Anyagor, and a professor also from American International University in Kuwait. So that's the internationalization element coming into it, and myself, Talib Ibad. So there are two institutions coming together, Northam University and American International University in Kuwait. So that's the contributors to this research. Solar road scope in the UK. Now, what is the scope of it? So the the idea is that we looked into what is the total area of road infrastructure which collects or to which the solar irradiance reaches from the sun. So the total road length in miles in the UK is 247,000 miles roughly. To keep it simple, 248,000 miles is the length of the road in the UK. Now, UK government has a budget allocated for the maintenance of this road infrastructure, which is 25.3 billion pounds up till 2025. The beauty of using roads as a surface area to collect solar irradiance or solar energy is you do not have to allocate land for for solar panels, like in, as we say, in solar farms. So instead of having solar farms, we could use that land for so many other types of developments, for human activities. We could have houses there. We could have some other developments over there, commercial areas, buildings, or infrastructure for something else, rather than allocating that land when the land is already very scarce. So roads are there anyway. So can we put our solar panels on roads while the traffic is running on them? Of course, it will have some implications. We will discuss them later on. So that's the beauty of it. Now, usage of solar energy, solar road energy has been applied or is being developed along these different technologies. For example, wireless charging for vehicles, road marking at night, e-vehicle charger, road de-icing, low power supply, road signals. So they can be operated with solar energy, solar road energy. One more click, please, Claire. Of course, the cost at the moment would be very high, capex as well as opex. I mean, capital cost as well as operational cost. But as the technology develops, and if the resources are deployed in this direction, then the cost will come down. A simple example I gave is that of computers. When they were not in use as much, they were very expensive commodity, excluding the inflation and all those factors. But now they are not as expensive as they are more and more in use. So same principle can be applied here as well. So the large scale manufacturing and application of solar roads can bring the cost down, both capex and opex. Yes, please. Now, the aim of research and objectives for this research piece of work I'm sharing with you is to assess or estimate the potential of solar roads in Great Britain by developing a numerical modeling, which I will show in a minute. And to achieve this aim, here are a few key objectives. Identify what road types are there. Some are major roads, some are motorways or B roads, A roads, small roads, city roads, and rural roads. So there are different types. So that categorization was needed to carry out this work. Another important objective is how much solar irradiance is reaching Great Britain in both contexts. What is the variation geographically across the country, and what is the seasonal variation? As we know, summers and winters, there's a substantial difference between the lengths of days in the two categories. So that's another angle to look at. Then calculate solar energy potential corresponding to each road type and for each season, dividing the year in two main seasons, summer and winter. And then finally, also look into what are other factors which will reduce the efficiency as a whole of the solar road system. This includes weather, shades as in trees, buildings, traffic, dust on the roads. So these are the factors which can also play a role in terms of reducing the efficiency. So these are the four main key objectives which were carried out to achieve this aim of the research. Yes, please, Claire. Now, here is the breakdown of roads. If we could, I know I can't move the cursor here. Motorway, yeah. So look at the top row, motorway. Yeah, thank you. Thank you, Claire. Very, very useful. Motorway, rural road A, urban road A, minor rural roads, minor urban road, and that is the total length of the road. So second row is basically lengths of all these categories of roads. And on the last column, we are having the total length of the road. Then road width, of course, it will vary from road type to road type. So I'm talking about the second row here, third row, technically speaking, road width, 0.022, 0.146, that is rural road A, and so on and so forth. So total road area, we are talking about that road length in one type or one category multiplied by its average width. That gives the area for all those roads. So number of, now that we have established the total road area, which is 2933.211, which is the last column, total fourth cell. Now, once we establish that, now, of course, the traffic would be running on it, and traffic would run on it in variation, peak hours of traffic of business, regardless of the peak hours of sunlight. So quite a few factors there. So what we have done is we have worked out total area which can be occupied or covered by traffic on average in a day in the UK. So imagine all the vehicles on the road have been put together, virtually or figuratively speaking, have been put together physically, bumper to bumper, and presume they are mostly cars anyway. And trailers, which are bigger in size, we have still treated them as a car. And similarly, vans or minibuses, we have still treated them as an average car size. That is going to give us a conservative value, rather than going for trailers and other large vehicles. So we have treated them all as cars. So the total area which has been worked out, which would be occupying motorway on average in a day, is 83,300. Similarly, other road types. So that gives us the total traffic area, or you can say traffic shade, which would be covering the total road network of the UK on average in a day at one time. So the exposed area minus the traffic shade is highlighted in green, and that is categorized for each road type. And finally, in the end, the last bottom right corner cell is the total area of the road, which will be collecting solar irradiance from the sun, excluding the traffic shade. Yes, please, next one. Thank you. So I need to speed up a little bit. So in order to work out the area, kilowatt hour, solar irradiance, which is reaching the sun, we consider these different large cities as regions: Newcastle, Manchester, York. When I say we, it is derived on secondary data. Secretary-based data, Secretary-based. London, Brighton, all these areas. And blue are representing the solar irradiance reaching from the sun onto the roads in summer. And in winter, obviously, it is substantially low because days are shorter and the light is not as much intensive and energetic. So that's the divide. Now, the 20% factor, which you are seeing at the bottom of each summer and winter, I explain that in the next slide. Next slide, please, Claire. Yes. Now, I'm sorry about the font size here. So if we look at the summer average and winter average for all these regions, the yellow is showing the total for England, Wales, and Scotland by accumulating all those individual regions. And 20% is the solar panel efficiency. So imagine solar panels have been spread out on the roads. The efficiency, how much energy reaches them and how much of that will be converted into energy. The internal system efficiency of solar panels is generally 20%. I call it conversion efficiency. So if you put all that together, you get those blue boxes at the bottom right corner. That is the total energy of the solar radiance that can be converted into solar energy by panels on the road. Next, please. So calculation summary, in other words, it would be total area exposed without shades and with shades. And this is where the shade of trees, buildings, cloudiness, dust, all those factors, external outside the system of a solar system, solar energy road system, that has been taught up to 25%. Top right gray shade area in white color, 25% that has been worked out based on different secondary data available. Now that 25%, 20% is the efficiency of solar panels. Putting all that to, and traffic area is already excluded. So putting all those factors together, the total energy that is worked out to be these green rows that you see. So it's quite a big number. We are talking about 1, 2, 3, 4, 5, 6, 7, 8, 9. So for 456 tera kilowatt hour we are talking about here. And that's what has been covered in the lower cells. So total energy and the factors which I said about 25% is also applied in the bottom column, bottom row. Total energy performance 75%, because 25% is going to be lost, so you're left with 75%. So the total we get is 442 terabytes. Not terabyte, sorry, I'm not in IT. Tera kilowatt hour, and after the shades have been applied, we are getting 333 tera kilowatt hour per year. Next, please. Now, if we compare that energy, for which there is a potential from solar roads, it is 346 terawatt hour per year is the demand of electricity in Great Britain. If we are calculating solar road potential without shades of trees and all that, buildings, etc., that is 442 terawatt hour, and other, if you include the shade, it is 333. Still, if we consider the shades and all that, being very, very conservative, that is the potential. So we can see in either case, in case of no shade considered, it is exceeding the electricity demand. And if you consider the trees, shade and all that, it is still not far off from there. Next one, please. So in conclusions, keep going, please. 96.42% of the electricity demand of the UK can be met by having solar roads. And other advantages, we will be much better off, a huge potential to reach net zero carbon agenda. And all these four sustainable development goals can also be contributed into, which are affordable and clean energy, sustainable cities, responsible consumption, and climate action. Of course, that can be another area to discuss and look into. So for simply, I have said here that these are the four main goals that can be contributed directly by this approach. Next one, please. Right. Now, this is the second piece of the research. The earlier one was solar roads, and this one is about solar paints, a new renewable technology. And it is at very much infancy stage. It is not something which has been applied to great scale so far. So experimental. So here again, the contributors are the same, except that I have got United Arab Emirates University here involved, and other than that, the other authors are the same. So next one, please. Pardon me. So the aim of this research is, again, similar to that of solar roads, but a little bit different approach. Pardon me. Solar paint. So what is the potential of solar paints? Imagine if solar paint is applied throughout the housing sector in the UK, which is roughly about 25 to 26 million households I'm talking about here. Of course, varying sizes, various types. So if they all are solar painted, how much energy can be generated? The potential I'm talking about. And that is the purpose of this study. And to achieve that, the key objectives are look into solar paint types, technologies available out there. What is the potential of each technology? Because each technology will have different efficiency. And what are the types of dwelling in the UK, and how can paint applied onto those different types of dwellings in the UK can potentially generate solar energy from the solar paint. Next, please. The assumptions have been made here. These assumptions are the areas which are where further research can be carried out to further or more precisely estimate the solar potential of solar paints. But for now, these are very, very conservative figures, so we would not be far off of the total potential which can be really there. So average standard height of the roof from the ground level is generally 2.6 meters. Average window area in the UK, Great Britain, is 0.55 meters square, half a meter square roughly. Roughly speaking, every room in a dwelling has one window. Some may be having two, some may be having none, depending on the storeroom or garage. And so there are 5 categories UK housing stock can be divided into: apartments, bungalow, terraced house, detached house, or semi-detached house. In these 5 categories, the average wall area, excluding the window and things like that, has been worked out to be 200 meters square, 253 meters square, 272 meters square, and 483 meters square, and 315 meters square per respectively in those 5 categories. Next one, please. Now, solar paints there are a number of technologies out there, but these two specifically are going produce electricity directly. Some produce even hydrogen, which is still very much surprised by technology, but that's still there in fancy stage though. But these two are the ones, these two solar paint technologies, quantum dot and perovskite, they produce electricity directly. And these materials which are used in these two technologies have been named after the materials which are used in these respective technologies. Quantum dot and perovskite, when the photons or rays of solar irradiance hit the surface of these materials, the photons, which are carrying energy packets in the rays of light, they excite the molecules or atoms of these materials, and electrons, voltage or electric charge is generated, and electrons begin to flow through the body of the circuit. And that's where the voltage, due to voltage generation, and from there electricity can be tapped. So these are the two technologies. Yes, please, Claire. So NASA has been employed as a secondary data source. According to that, we can see there is a column of months, January, February, March, all the way down to December. The daily vertical solar irradiance is 1.7, 2.1, so on and so forth, right to the end for December 1.56. That is daily. In every month, there are a number of days, 31, 28, 31, 30, all that, multiplying by days. And that, so the total solar irradiance per kilowatt meter square per day and per month has been calculated for each month on average based on NASA's secondary data source. Next one, please. Like I said before, dust, cloudiness, and other elements like DC and AC cables. So all these factors further reduce the potential of solar energy from the solar paints. And these all have been catered for, the figures have been catered for very conservatively so that the estimation is not way over. In fact, it will be, and we are underestimating actually the potential. So if you start it all up, it comes out to be 25%, or in other words, 0.25 is the multiplying coefficient factor, which will be used in the equation, which you'll see in a minute. Next one, please. Next one, please, Claire. Hello? Oh, sorry. Yeah, it's working. Sorry. Right. So now the efficiency of the technology itself, the amount of energy which gets into a solar paint, and how much electricity is generated on the other end of it, just like engine efficiency of a car for diesel engine or anything. So the efficiency of quantum dot QDSP technology is 8%. Again, very conservative. And efficiency of Pravoski, I can't pronounce that word, my apologies. So the PSP is 14%. These are the percentages: efficiency, dust, cloudiness, air, temperature, pressure, rain, all those factors which I was talking about. That is 0.25. And these percentages, and using this formula, the areas, average area of the dwellings for 5 categories is already mentioned in my previous slides. So we multiply all that together by using this equation, then the potential of solar paint energy can be calculated by using the formula, and the next slide shows what values have been achieved. If you look at the top, the total energy, could you undo the graph, Claire, please? Just one step back. Yeah, cheers. Thank you. So the total energy from homes in a year, kilowatt hour per year, for apartments is roughly 28,000 kilowatt hour per year. For bungalows, it is 8,000, well, roughly say 9,000 kilowatt hour per year. That's the demand of bungalow for electricity per bungalow in a year. So this is done for all the 5 categories, secondary data, and the calculations for quantum dot solar paint and perovskite solar paint has been calculated for each type of dwelling in those figures there. And if you notice, the potential is not far off the demand. In some cases, it even exceeds. So for both the technologies, for each category of dwelling type in the UK, the results are there, and they are presented graphically as well as follows. Yes, please. Next one. If you look at this graph, on the x-axis, we have dwelling types: apartments, bungalows, terraced houses, detached, and all that. On y-axis, we are talking about the energy, electricity, and the color codes are showing for the demand for these houses, electricity for each category per house, per dwelling. And then we have quantum dots and perovskite as well. If we notice that the perovskite is superseding as a technology even superseding even or even exceeding the demand of electricity for each dwelling type. Whereas the quantum dot is just about meeting bungalows and terraced houses, whereas for others it is way below. That also would depend on the availability of the surface area, and also the technology efficiency itself. So quite a few different variables are still hidden in there that can be explored in further research projects. Next one, please. These are the references, and the potentials are already calculated. So I have managed to save a few minutes. If somebody has any questions, then please go ahead. Thank you for doing that, Claire, for me. I appreciate that.